Hey there, folks. Back here with another video in our uh, introduction to limits. And where we're at, folks, is we're kind of at the end here in our introduction to beginning to understand what it means to be a limit, folks. I think I've given you everything I can give you in terms of actual theory, in terms of what it means to be a limit, in terms of continuity, looking at it with respect to discontinuity, and the case for infinite limits, and the case for limits at infinity. Right? I've looked at all the theory related to those concepts in my previous videos. Where we are at is perhaps a moment where we want to go back now and kind of summarize everything we've learned and put it into some sort of technique. All right? And what I have for you today is a summary of that technique. Let me bring this up. Right here I have a bit of that summary, folks, for that technique. I want to go through these set of notes with you where we discuss this summary. If you haven't put together your own technique yet, this is where we want to kind of take what we've learned over the last few videos and start to say, okay, what does that give us in terms of approaching the value of a limit? And in general, this is how I approach limits. Limits are interested in behavior, and it depends a lot on functional analysis, a little analysis of behavior for a function. We're being familiar with the case for the limit that you're being asked to evaluate, and being familiar with the function itself is all going to play a role in helping you to evaluate the limit. All right. Now, where I begin here in my notes is I do begin looking at, as I said here, just clarifying between one-sided and two-sided limits, and being able to say that a limit does not exist as a limit. All right. In the case of one-sided limits, where we could actually think of A being any value, and what I mean by that is we could think of A also being the case for plus or minus infinity. All right. You could also consider those situations in that mix. Right. And I think I might change this here a little later in the notes, but we won't start with that now. I might say any real value or plus or minus infinity there, but we'll take care of that at the end. A one-sided limit is denoted here with plus or minus superscripts used on that value of A, right? We can see that as our notation. And what we say here is that this limit can always be evaluated, right? When approaching one-sided limits always can be evaluated. You're not allowed to say with them is that they do not exist in terms of being a limit. The only cases you can say that a limit does not exist as a limit is the case for a two-sided limit, where we don't see that subscript on the value of A. Right? When we don't see that subscript on the value of A, right, we have a two-sided limit, and that limit could have the potential for not existing as a limit when the left-hand side limit and the right-hand side limit don't agree with each other, when they're not equal to one another. Right? In that case, right, we can say that this limit does not exist as a limit. Right? The left side limit and the right side limit, however, will always exist as a limit. Right? We have seen that in our study, and we should really start by taking note of that. Right? To realize when is a limit's value or evaluation possible, and when can we say that it's just not going to exist as a limit. Right? That is important. So always be on the watch out for that when evaluating limits. Right? To begin with, though, when presented with a non-piecewise limit, right, what I do in my strategy, right, is I always first check the nature of the approach, one-sided or two-sided. Right? I'm going to want to keep this in mind for what could potentially happen a little later on down in my evaluation. Right? But in either case, once I take note on the direction of the approach, I consider just performing a little substitution method. Right? I always evaluate my function at the value of a and consider applying a little substitution method to the calculation of my limit. Right? And I say here I attempt it because we don't always get the result that we would expect from substitution. Right? Substitution method supports when our value f of a exists as a real value. And we have continuity in our function f at a. Right? Substitution method does not support the other results that we could also have occur. However, it is evidence for and can be used for evidence for these other cases. Right? Well, the result of a substitution method. Right? But when I always begin with attempting some substitution method and analyzing that result of f of a. It is a bit of a functional analysis, but it's a bit of a functional analysis in the context of the limit. Right? And there are three possibilities that we've encountered for f of a. Right? It either exists as a real value, it either produces an undefined value, or it's the case where we produce what would be called an indeterminate value. Right? We could have those three cases occur when we begin to evaluate a limit, and our first step in that evaluation, after considering the direction just to begin with, is attempting substitution method. F of a could exist as a real number. It could give us an undefined result, or it can produce what we call as an indeterminate result. Now, if the evaluation of f of a exists as a real value, right? Well, that's where substitution method applies and works and supports our result and says that the limit as x approaches a for f of x must be equal to that value f of a. Right? We have what's the case for continuity. Right? F is going to be continuous at x equal to a when we see this result. And if we look at our analysis of f as a function at the value of a, we should see that continuity in this case of the evaluation. Excuse me. That is what we hope occurs when we attempt substitution method when evaluating a limit. We hope that it is as easy as just evaluating our function at that value of a. However, I often joke in our study, those are the simple cases, right? Those are the cases that really a student of algebra can stumble upon with just a little bit of algebraic process, right? That is often not what occurs. What often occurs in our study is one of the two other cases. One of the cases of either encountering an undefined value or the case for an indeterminate value. And we have to be prepared for those. Those are the cases that are going to leave us guessing at the end of substitution method and having to further our technique. All right. So what we take note is if we encounter, if you keep in mind, the value of f of a producing an undefined value when we attempt our substitution method, what the graph of f must contain at that value of x equal to a is a vertical asymptote. When we encounter undefined values in a function f at the value of a, right, what we have occurring at that value of x equal to a is a vertical asymptote in the graph. And as x approaches a, we understand with or without, as x approaches a, that vertical asymptote from either the left or the right or even from both sides, f of x does one of two things. It either increases or decreases without bound. Right? In the case of one-sided limits, right, we either go up towards positive infinity or down towards negative infinity, and we have the case for simply an infinite limit. In the case of a two-sided limit, though, the approaches from either direction can actually be opposite each other, right? Whereas we approach a vertical asymptote, the left or the right could actually head in opposite directions, one towards positive infinity and the other down towards negative infinity. In that case, we would actually say the limit does not exist as a limit. Otherwise, if both head up towards positive infinity, we can say that it exists as an infinite limit that heads towards positive infinity, or if both head down towards negative infinity, we can say the same, is that it exists as an infinite limit that heads towards negative infinity. Right? But when looking at the two-sided case, right, there is the potential that it does not exist when the one-hand directions, the one-sided directions, the left and the right side, approach different values. Right? So when you encounter an undefined result, you take note of the direction of approach. Is it one or two-sided? If it's one-sided, you know the answer is going to be plus or minus infinity. And what we learned is you can then perform a functional analysis on the function f at or near the value of a in the direction of that approach. And through a numerical analysis of sign, we were able to determine what direction we were approaching, positive or negative infinity. Right? It turned into this analysis of sign. In the two-sided case, you still have to go back and look at both the left and the right-hand approach, and you have to produce that analysis of sign for both sides. Right? And you're going to go back and do that for both the left and the right-hand approach. And both of those are going to exist as either plus or minus infinity. They're going to exist as an infinite limit. It's whether or not those left and right-hand approaches equal each other, right, that we can go on to say that we have a two-sided approach that either equals or does not equal. If they equal, it does exist as an infinite limit, and if they do not equal, it does not exist as a limit. All right? Take a quick break here. I need that. There we go. All right, folks. I'm glad I took that moment to break. I was able to also catch my wife carrying in the groceries for the week, so I was able to help her. I did break. I did want to add something here at the end, just to go back and again note on how we evaluate an infinite limit, right? It is an analysis of sign. It's a numerical analysis. We take a look at how does f behave near our value of x equal to a with respect to sign, right? In this summary, I don't get into those little details. Again, that's back previous in the study. Like what we're looking at here is more or less a summary of process. All right, that's one thing we want to keep in mind here. But I did want to remind you that when you do see f of a, an undefined result, you can expect either an infinite limit in the case of one or two-sided limit or one-sided limits. And in the case of a two-sided limit, you can expect an infinite limit, or the case for does not exist. How you determine the sign in the case of the one-sided limits is through a numerical analysis, right? And a numerical analysis of our function f near the value of x equal to a. From values less than a if we're approaching from the left, and from values greater than a when we're approaching from the right. Right? Keep that all in mind, and that's previous in the analysis. And then the third case we discussed earlier in our theory here was that when we perform an evaluation, we do have to be on the lookout for when f of a produces what we call an indeterminate form. Right? When we attempt to perform a substitution rule or method, there is the potential that the result is going to be what we call an indeterminate form. And we saw back in the theory that there were several cases for that form. Well, at the moment in our study of calculus, what we really rely upon is simply just trying to rewrite our function. Is there a way to express our function to remove some of the indeterminate, and I hate to use the term factors, but that is sometimes what the process involves, is trying to find those factors that are causing the indeterminate behavior and removing them, right? We talked about the case for removable discontinuities, right? These are these situations where substitution rule produce these indeterminate form, right? So at the moment, you really just want to try to rewrite your function, and I showed you a lot of examples of that in class, and then we referred to this back in the notes. We've seen this done several times in the notes, particularly with the rational form at the moment. What we're going to develop later on at the end of our study of the application of the derivative, which is a few chapters away, a couple of chapters away, is we're going to be introduced at L'Hopital's methods, where we're going to see ways of evaluating these indeterminate forms using derivatives. All right. And we're going to develop some methods for evaluating indeterminate forms that go above and beyond just rewriting f. All right. So that is all later on in the study. In addition to this general strategy, right? Oh, let's be careful here. Where I go in the notes, where I go in this note set, is these three results above, right? When we think about what I've just discussed above, this is all the instance where I'm talking about a piecewise, non-piecewise limit, right? A limit that doesn't involve a piecewise function, right? We also saw back in the notes, particularly when we were being introduced to the understanding of a limit very early on, the cases for piecewise defined functions and limits involving those piecewise defined functions. Well, there is a bit of strategy there when we encounter those, right? In the event that we have a piecewise function and we're looking at a piecewise, perhaps, limit, right? For the value of the limit, right? If a is a value that's within the, is a real number within the domain bounds of a particular behavior, then that limit, right, should be able to be evaluated with the techniques given above. All right? If the limit value at a doesn't exist at a value that is a boundary between two different behaviors in your piecewise function, then you just evaluate the limit using that behavior right, where it exists in the domain, right, where that value of a exists in that domain of that behavior, and evaluate that limit using the techniques that we mentioned previous here, right? However, if that value of a, right, is a real number of bound, right, between two different behaviors in that piecewise function, what you then need to do is look at it with the one-sided limits. You need to consider what's the behavior on each piece. What's the limit behavior on each piece, right? You need to look at both the left-hand side and the right-hand side approach. On the left-hand side, you will have one behavior. On the right-hand side, you will have that the second behavior, the behavior that's greater than that left-hand approach. And if those two pieces of behavior don't behave the same way for the limit, then you can say that that two-sided approach does not exist, right? Otherwise, the limit will exist if both the left and the right-hand approach are equivalent to one another, if the results agree with each other. So that is the case of a piecewise, right? In a piecewise function, you basically use the techniques above unless the value of a is a boundary between two different behaviors. And then you have to break it into both the left and the right-hand behavior and analyze for the potential of non-existence as a limit, right? Using that two-path test for existence. So I also mentioned that in general strategy, right? The case for when we see piecewise functions. Now, in addition to all of this, right, there is also a list of generic rules, or what we call limit laws, right, that we can apply when questioning the evaluation of really what we might say is a bit more of a complex combination of known function types. And I got an example of that down below. Right? But we do have a collection of rules, right, that are called our generic limit rules, or what I might call limit laws. Right? These are our limit laws, just in general. Right? In this law set, in this rule set, C is going to be any constant. When you see little c, it's going to be any constant. When we encounter the value of little n is going to be greater than 0. It's going to be a positive value, and it's going to be an integer, like 1, 2, 3, 4, 5, right? And we're going to let x sub a, the limit as x approaches a for f of x, and the limit for f as x approaches a for g of x just be generic limit statements where we assume the limit does exist, right? Including the cases for the one and the left and the right-hand side limits, the cases for the one-sided limits. Right? I know the notation involves the two-sided, but this is also true for the one-sided limits. Right? Now, the first rule on the list essentially says if you take the limit of a constant, the result is just the value of that constant. Any limit of a constant is just the value of the constant. The limit as x approaches 2 pi for pi is just pi. Right? The constant being pi. The limit as x approaches 0 for pi is just pi. Again, the constant being the value of pi. Right? The limit as x approaches negative infinity for the value of 2/3 is 2/3. Right? Again, the constant being the value at 2/3. The limit of any constant is just the value of the constant itself. Right? That's the first of our limit laws. The second is called the constant multiple rule, which involves having the constant multiple of some function f. Right? Essentially, the constant multiple of any function can be factored out of a limit. Right? You can factor out from any limit statement inside the argument a constant multiple. right? If you can identify a constant multiple inside the argument of a limit, you can simplify that limit by factoring out that constant multiple. The limit of 2x is 2 times the limit of x, right? 2 being that constant multiple we could factor in that case. All right? The third rule we see here is called the sum. Did I put a difference rule here? Oh, I did not. Let's set that up here. This should be a sum or difference rule. So let me change this sign. This is true for sums or differences. I think we ought to make that clear. Right? Otherwise, we have to think of function g of x as being an opposite of some other function, which is really not what could be stated above, or is stated above clearly. So I think this might help clarify. Let's make those plus or minuses. This is called the sum or difference rule of limits. And essentially a limit will distribute. It will distribute itself across sums and differences. It'll distribute itself to the first function in the sum, what we might call function f, and it will distribute itself to the second function in the sum, the function we might call function g. And when it distributes, you'll be left with the limit for the sum or difference of the limits for the individual functions. The limit of a sum or difference is the sum or difference of the limits. Right. The limit operator will distribute across sums and differences. We also see that for products and quotients. The limit operator, right, does distribute across the multiplication of two functions, as we see in the fourth law here, right? The limit of a product is the product of the limits, right? Or, as we see in Rule 5 here, the limit of the quotient is the quotient of the limits, right? Now, with the second case being where the limit as x approaches a for g of x, this end result not being equal to 0. And we would have to assume from that g of x itself is also probably then not the 0 function, right? But the limit operator, not only can you factor out constant multiples from the operation, you can also distribute it across sums and differences, products, and quotients. We see that in all four rules here. All right. Rule 2 through 5. Now, in addition to that, we round out the list with how that limit operator will also behave. It will factor itself into powers of a function. If you have a function raised to a higher power of n being what? An integer value that's greater than 0, right? The limit of that power of f is just the power of the limit. The limit will factor itself into a power function, right? Or, where you'll also see it bring itself in as a factor, is into a radical statement. The limit operator of a nth radical is equal to the nth radical of the limit. The limit operation will bring itself into the nth radical, right? When we have the radical of a function, it will, in a sense, become a factor within it, applying itself as an operator. Now, this is all provided that when we're thinking about this scenario here, that function f of x is a positive function, a function that is, I should be careful there, not greater than 0. We should really say greater than or equal to the 0 function when n is even, right? It can be Doesn't have to meet that condition, though, when it's odd. Only when it's even, because we aren't going to acknowledge the imaginary results. We only want the real results of this. Right? Those are some generic rules. And those are generic rules we can follow when we face more complex situations in our functional analysis. I look at this case here. Excuse me, I'm going to have to take another quick break just to get something to drink for my voice. I'll be right back. All right, I'm back. I'm glad I took that quick little break. I was able to get a glass of water here and notice a little error in my problem. I wanted to make sure that was at 4x, not 2x. Hopefully you worked through it. Well, you may have worked through it with 2x ahead of me here, but let's look at it for the case of 4x. I did change that around in the work just to have it work out a little nicer in the end. But if we take a look here, we are evaluating the limit as x approaches a real number 2 for what is a complex combination of different function types here. And to begin with, we have a constant multiple of what might be a complex combination. We have 5 times this complex combination where if you take note, we do have the exponential function e to the x, right? It's being multiplied by this radical, the square root of x squared plus 4x plus 13, right? Where in the square root of x squared plus 4x plus 13, we have a quadratic underneath that square root operation, right? We have some complexity here in the function we're evaluating with our limit. If we think about technique, we could attempt substitution, and we're going to see that that result would not be wrong, right? But we want to have a little support, perhaps a little confidence in our argument. And we can use the rules above to break down this argument, right? For why substitution rule might work well for this limit, right? If we just go through some application of the rules above, as I already pointed out, there is a constant multiple of 5 in there, so we can factor that out. Right? So I bring that all the way out in front here as a constant multiple. But then that limit will just distribute across the product of e to the x with the radical. And that's what we see going on right here. And then even more so, what do we see above is that that limit will distribute itself into the radical. So when it distributes itself to the square root statement, it really is just distributing itself to the quadratic function underneath that square root statement. Now that quadratic, we could go as far as distributing that limit to each and every term, right, within that argument. However, we also can feel rather confident that that is a quadratic function and that is a parabola. And that must, being a parabola, must be continuous at the value of x equal to 2. So substitution is well supported here. And we can see that we end up with the square root of 25 if we apply it underneath that radical. And similarly, outside that radical, with the limit as x approaches 2 for e to the x, that's simply the exponential function e to the x, which we also know is continuous, at the value where x is equal to 2. So it's easily supported with substitution rule and equivalent to the value of e squared. Now the square root of 25 we all know is 5, and 5 times 5 is 25. So in the end, we do have the final result of 25e squared for the value of this limit. The same result you would obtain through just simply substitution. But if we want to feel a little bit more confident in why that substitution works and support continuity of this function at the value of x equal to 2, right? These rules, these laws that we apply along the way in the evaluation, right, can be that support. All right. Now, what I've stated above with these rules does also work for the case of limits at infinity, right? However, the technique stated above here, right, initially, where we go through this technique of applying the substitution method, we are considering A, right, as I should say, a real value. And maybe I should say that here, because what we're saying above does apply to infinities. When presented with a non-piecewise limit, we should maybe say where A is any real number value. So what we're discussing here is the case in this technique down below, right? In this technique described here, the summary is the case for not being a limit at infinity. All right, so take note of that. These limit laws, however, do work for the case for limits at infinity. All right, and I probably should say that in here. Maybe I should say including cases for limits at infinity. All right, where what do we see happening again is that x is approaching, right, the values of plus or minus infinity. All right, so we might add that in there, that these laws do work for that particular case. Right. However, to go above and beyond that, we don't really give much else in terms of limits at infinity. Oh, this is our conclusion for the previous problem. So what also exists are a set of fundamental results that we can apply for limits at infinity. All right. These are some limit laws at infinity, is what we're going to call them, right, or what they're called. And similarly, n is going to be a positive integer, right? B is going to be any base where b is greater than 0 and b is not equal to 1. And C is going to be any constant in the following rules here. And the first rule, again, goes back to that constant rule. The limit for a limit at infinity for a constant value is also just a constant. Right? Whereas the limit, as x heads to plus or minus infinity, for the power of x, to the positive integer power of x, is going to be either plus or minus infinity, and that is an exclusive plus or minus. What it depends upon, right, is again a bit of analysis of n behavior. Remember, a lot of limits at infinity is understanding the n behavior of your function, and it's understanding the n behavior of x to the nth power. When n is even, n's are going to behave the same, both up or down, but that again depends upon some other factors, right? And when n is odd, they're going to point in opposite directions, and again, that depends on other factors. So I leave this rather general. It is going to require a further analysis, right? An analysis of sign, where you're going to have to rely upon n behavior, but nonetheless, you know it's going to be an infinite limit, plus or minus. As for the limit as x heads to plus or minus infinity for 1 over x to the n, if we were looking at the reciprocal of the power of x, where n is a positive integer power, that's always going to head to 0. That limit at infinity is always going to be equal to nothing. Right? And we can say that exactly. It is not the case for an infinite limit. That limit at infinity is not an infinite limit. It is actually the real value of 0. Next, we consider these cases. Now, these cases you want to keep in mind, right, are related to being the nth radical. And probably I should say that in here. And when we talk about this value seen here, we are talking about the nth radical of x. We are talking about the nth root of x. And in this case, we're talking also about the nth root of x. Heading towards, in this, if you'll notice the difference, it's the existence of a particular limit at infinity. This case, when n is even, in this nth radical of x, we only have the case for the right-hand approach, or the limit at positive infinity, I should say. The limit for the left-hand approach at infinity. And it yields positive infinity as a result, because our function doesn't exist in the negative direction for the left-hand approach at negative infinity. However, when n is odd, that approach does exist, both the left and the right approach at infinity, where we approach both positive and negative infinity. All right. So when n is odd, we can consider the limits at infinity for both plus and minus that nth radical of x. And it's going to be, again, an infinite limit that's going to have to be determined by sign analysis. Now, for any exponential function, right, like b to the x or e to the x, b being any base, when you go in the negative direction, right, when you go all the way down to negative infinity, remember, it gets closer and closer and closer to 0 in an exponential. Right? That limit at infinity for approaching negative infinity, notice we're only approaching negative infinity, is equal to 0. When we approach positive infinity, right, for that exponential, that is when we become an infinite limit and we approach positive infinity. As for a logarithmic situation, right, for a limit at infinity, right, we only have the case for a limit at positive infinity. And maybe I should highlight that here. I did not do that in this case. We also only have the case for a limit at positive infinity, where for any logarithm of base b for the argument of x, we're going to head off to positive infinity. All right. Those are some general rules for limits at infinity that we can also keep in mind. What we do notice is that we didn't really include any rules for the trigonometric functions for limits at infinity. And what we say there is that they don't have limits at infinity. The sine, the cosine, the tangent, the cotangent, the secant, and the cosecant, their values as we head off towards positive and negative infinity oscillate over intervals that are bounded by plus or minus infinity. Well, sorry, plus or minus 1. As we approach positive or negative infinity. The sine function just continually bounces between plus or minus 1 as we head off to positive infinity. So we say these limits don't exist in these situations. And then, to help us a little further with some of the complex forms we're going to encounter, we can say the following about polynomials and rational functions. Here we consider the limit of a polynomial function at infinity. A polynomial function that takes on the form, right, that we're familiar with a polynomial, a sub n x to the nth plus this pattern of degrees of n reducing by 1 all the way down to a sub 0, that familiar pattern of a polynomial. Well, the limit of any polynomial is going to be equivalent well, at infinity is going to be equivalent to the limit for its leading term. That's what we're highlighting here, is that this polynomial's limit will be equivalent to just this limit of the leading term, a sub n x to the nth. And if we apply our limit at infinity to this term, well, that a sub n would play the role of a constant multiple, and we would have just the limit as at x heads to infinity plus or minus for strictly x to the nth power, which is summarized in the list rule above, right? For x to the nth power, that's going to be an infinite limit. All right, folks, let's see if I can wrap this up in the next few minutes. It's getting to be a long video. So let's see here. The other rule we had, folks, that I was presenting right below the polynomial here was the limit at infinity for a rational function. If you take note, a pure rational function is really the quotient of two polynomial functions, right? So if we take the two polynomial functions, one in the form where we have a sub n x to the nth all the way up to a sub 0, and we put it over a second that might start in the form b sub m x to the nth and have its values go all the way, decrease in degree all the way down to b sub 0. If we think about those in some sort of rational form to form a quotient, right, this argument of a limit of a rational function, then the limit at infinity for that rational form is nothing more than the limit at infinity for the quotient of the leading terms. P of x's leading term is a sub n x to the nth. Q of x's leading term is b sub m x to the nth. And if we think about those two polynomials in ratio with one another as we go out towards positive and negative infinity, the n behavior is going to be described by the same n behavior described by the ratio of the leading coefficients. So the limit of p over q is equivalent to this limit here. Where if you analyze this argument here, a sub n and b sub m are just a constant multiple in ratio with each other that can be factored out of x sub n, or x to the nth over x to the mth. And x to the nth over x to the mth, well, that's a power of x that can be simplified into the power of x to the n minus mth.
There are no timers set.
Sorry, Alexa. Apparently I'd set her off. My apologies. Startled me. So we want to be careful with x to the nth minus, well, where was I? Sorry. If we take note, all of this simplification is supported by the rules above. A sub n over b sub m, well, the limit will distribute across to the numerator and denominator. The a sub n and the b sub m will factor themselves out of the limit as constant multiples. It can be formed into a ratio out in front, a sub n over b sub m. And then the ratio of x sub n over x to the mth can simplify into x to the n minus mth. Right? Where we could factor the limit out, or back out of that ratio, and present it this way. Now, presented as x to the n minus mth is a little misleading. If you perform the difference, you will have an x to a certain power, either a positive or negative power. Where to evaluate this limit at infinity at the end of this result, we will go back and potentially rely on these results seen here. Right? It's either going to be a limit at infinity. That limit at infinity is either going to be an infinite limit, or it's going to be equivalent to the value of 0. Right? Pending that power of x in the end. Now let me give you a couple of examples of this. Consider a polynomial. Here's a polynomial. Right? What the polynomial rule says, here rule number 1, is that this limit is the same as just taking the limit of negative 5 times x to the third power. It's just the limit at infinity, negative infinity, for the leading term. And if we analyze that limit, right, that negative 5 I'm probably missing that. I probably should say that here. Let's say this is equal to the limit as x heads to negative infinity. Give myself a little space there. But when we apply the rule, it's going to be negative 5x raised to the third power. It's going to be just the limit as x heads to negative infinity for the leading term, where that negative 5 is a constant multiple and can be factored out using the constant multiple rule. And we're left with the limit as x heads to negative infinity for x cubed. Where there we should understand the left end behavior of x cubed points down to negative infinity. It's the cube function. That's in our library. We should understand its left end points down to negative infinity. It moves like that through space, right? If we go back and look at its graph. So the limit as x heads to negative infinity for x cubed then is going to be equal to negative infinity. And when we think about our initial limit, it is going to be negative 5 times the limit as x heads to negative infinity for x cubed, which is really just the value of negative 5 times this direction that's heading in the negative direction, which in the end, if we think about it loosely, that is going to head us off towards the positive direction. Right? We know the negative of this negative is going to make it back into a positive. And 5 times something that's heading off in the positive direction is just going to head off to positive infinity. And positive infinity becomes our result because of the double negative in the above statement. That is how that polynomial rule works for limits at infinity. The limit of this polynomial is really just the limit of the leading term, where you then can use the constant multiple rule here and evaluate just the limit of this power of x, which you know is going to have to be either positive and negative infinity, which leads you to really just an analysis of sign. And here our analysis of sign leads us back to positive infinity with that constant multiple factor in negative 5. Right? Even though we're looking at left end behavior. All right? Now here's an example. Well, that's our end for that result. And here's an example of a quotient or a limit at infinity for a rational function. Notice that rational function is just really the ratio of two polynomials. And we want the limit at infinity for this ratio of two polynomials, this rational function. And what the rule above states is that this is really, right, for this ratio of two polynomials, the limit equivalent to the ratio of the leading terms, 2x squared over x cubed. So when we think about the limit of this rational function, it's just really the limit of the ratio for the limit at infinity, the ratio of the leading terms. Now that 2 is a constant multiple, and we can factor that out, and we're left with simplifying x squared divided by x cubed on the inside of the limit. And really that is just x to the 2 minus 3 power following our power rules. So that leads us to x to the negative first power, which is just 1 over x. And what do we know about the limit as x heads to infinity for 1 over x? Well, that in the above rules, don't want to go too far. The limit as x heads to infinity for 1 over x to any power of n, where n is a positive integer, is equal to 0. So down here in our result, this limit as x heads to infinity for 1 over x is just equivalent to 0 from the rule above. So the constant multiple of 2 times 0 is really just equivalent to 0. And there we're using our limit at infinity rule for a rational function. All right. These are just some limit at infinity rules that weren't presented earlier in the theory, folks. I want to present the rules here at the end in the summary because I don't want you just relying on the rules. All of this limit at infinity stuff does pertain to end behavior. What supports all these rules is the end behavior of these different function types. Right? So to emphasize that, I did introduce limits at infinity with an analysis of end behavior, where later on, if we just want to summarize it, we can gather a collection of rules for limits at infinity. And the same goes true for our other generic limit laws that we saw above. Right? Our analysis of limits really should be a functional analysis. Our evaluation of limits should involve a functional analysis. No set of rules is going to get us to the end in every single case. So it's developing that, the strategy needed in that functional analysis is what needs to come first, then followed by some rules that are also going to help us along the way. And that's what I'm presenting here in this summary, folks. So I hope all of that was clear. I do think I also noticed in here I have to run a spell check over this section of notes. I do think I had some additions along the way where I need to run another spell check. And then I'll post these notes up for you folks so that you have access to all this in the class. But I hope you're doing well. I think I got a couple more, and I hope quicker videos, because I'm just going to look at a couple of one example in each video, where what we're going to get into is the precise definition of limits. And we're going to introduce what are called our epsilon delta definitions. It's going to be a lot of theory there, folks. And to avoid the videos becoming too long, I think I am going to try to keep them short by doing one at a time, right? And trying to work in one example at a time, because the examples can get long. All right, so we will see that in the next video set, but we're right at almost an hour, so I'm going to stop there, and I will see you folks all in class this week. See you then.